Welcome back. So today we're going to look at how to write parallel programs in shared memory systems. And we're going to use something called OpenMP. Okay, so let's first recall how the shared memory architecture. Okay, so here we have a bunch of parallel processors, right? And all the processors are connected to a common piece of memory. Okay, so there's a single address space. And this means that whenever one process can access a variable, then all of the other processes can also see the variable. Okay, so this is in contrast to the distributed memory architecture that we talked about for MPI, where there you actually break the memory into different pieces, right? And then different processes can just see their own piece of memory. And if they want to access another piece of memory, right, then they need to send a message to the appropriate processor. Right, so here we don't need to send any messages because every process can see every memory location. Okay, and the main advantage of doing shared memory programming is that it's more convenient and it's easier to write than distributed memory programs. Okay, and that's because, for example, when we did MPI, right, we saw that whenever you want to get a piece of data, you actually need to coordinate between two processes, right? Because you need to send a piece of data, and the receiver also needs to receive that piece of data, right? Now, if you don't have that coordination, then the processes are going to block, right? And then your program doesn't work, right? And also, you have to keep track of where the data is, you as a programmer. Okay, for shared memory programming, it's much simpler because all the data is there, accessible to all the processes. Okay. Another advantage to shared memory processors is that because everything is sort of so the shared memory systems tend to be of a smaller scale than distributed memory processors. Distributed memory systems. Okay, for distributed memory, you could have a gigantic system with thousands or even millions of cores. Okay, whereas for the shared memory systems, usually you have far less processors. You might have a few dozen, maybe up to a few hundred. Okay, but because you have fewer processors, then they're usually more directly connected to each other, and so you have higher bandwidth between these processors. Okay, so you can often achieve higher performance per processor at least. Okay, on these shared memory processors. Right. Overall, you still get better. You get greater aggregate performance on a large distributed memory processor. Right. But if you look at the amount of performance per processor, right, then it would be higher, or it's often higher on shared memory processors. Now, a downside to doing shared memory programming is that the programmer needs to be careful about different types of bugs, especially concurrency bugs. Okay, and so we're going to talk about that somewhat today. And then for the next lecture, we'll get into even more details about these concurrency bugs. Okay, so let's look at some different ways of writing shared memory programs. Okay, so the first way is to directly use threads. Okay, so this is done, for example, in the pthreads library or the Java programming language. Okay, so here the programmer takes a big program and he breaks it into little pieces. Each of which is a thread, and then these threads can execute in parallel, and the threads can also access shared data. So the advantage to doing this is that it's a very general way of writing a parallel program. You can basically do anything you want. However, because it's so general, then the programmer needs to be responsible for many things. Right? He needs to manage everything. For example, synchronization between threads, creating or destroying threads. So it's a lot of work for the programmer. Okay, another way to write shared memory programs is using like a specific parallel programming language. Okay, a language specifically designed for parallel programming. Okay. Now, this can be a good option because you can get good control over your threads, and you can get good performance. But the problem there is that you would have to for example, design a new compiler for this language. Okay, so there's a lot of work that goes into writing a new programming language, right? And also programmers have to learn about the new language. So that's also hard. Okay, so a third option is to use something called compiler directives. Okay, so for example, OpenMP uses compiler directives, right? And in fact, this is the most popular option right now. And the main reason is that these compiler directives are just, basically you just write a normal sequential program, let's say in C or Fortran or something, okay? And the compiler directives are just little annotations, okay, very simple annotations that tell the program when you want to do certain things in parallel. Okay, so really, the programmer doesn't need to learn all that much in order to write parallel programs. Okay, and you can also get very good performance, and also the compilers. It's somehow easier to design a compiler for something using compiler directives than for a completely new parallel programming language, for example. Okay. Now, even though the programmer is using just these simple directives to control the parallelism, underneath everything, right, underneath the hood, the program is still running using threads. Okay, but the difference is that the threads are being managed automatically by the runtime system. The programmer doesn't need to worry about that. Okay, so yeah, so these compiler directives are very easy to write, as you'll see. You do lose some flexibility, right? So it's not as general as, for example, using threads. Okay, but basically, in most situations, you can do what you need to do. Okay, and yeah, and there's also less changes required to the compiler. And this is by far the most popular option for writing shared memory programs nowadays. Okay, now before we get into OpenMP, I want to just talk about the difference between processes and threads. Okay, so we can parallelize either using multiple parallel processes or multiple parallel threads. Okay, so then what is the difference between processes and threads? Well, for example, MPI is going to have multiple parallel processes. Okay, so each process is a separate program. So what that means is that the program has all of these components shown down here. Okay, it's got code, of course, right? It's got a stack, right? And it's got a heap. Okay, so heap is like the memory that this program is using. Okay, and the thing about and if you run several processes at the same time, right, then they don't have access to each other's heap, right? If you have a different program, right, that program can only access its own heap. It can't access the heap from some other process. So therefore, if you want these programs to share data, you're somehow going to have to transfer the data from the heap of one program to another program's heap. Okay, so for example, in MPI, this is done using these send and receive functions. Now, for threads, right, so threads is what OpenMP uses. Okay, so in OpenMP, you don't have multiple parallel processes, you have multiple parallel threads. Okay, and the difference with a thread is that all of the threads run within one process. Okay, so you have multiple threads within one process, and they're executing different portions of this piece of code. Okay, so the threads can do different things, right? Because they can be at different portions of the code. Okay, and the thread, they also have their own memory in the sense that the thread has its own stack, right? So the stack is going to keep track of like the automatic variables and the function calls that each thread has made. Okay, so different threads can be calling different functions, so they have different stacks. However, the threads do share something, which is that they, since they're running within one process, all the threads can access the heap memory from that process. Okay, and so in this way, this is how different threads can share the memory, right? Because they can all access this heap, and if I write to the heap and you read from the heap, right, then we've managed to communicate with each other. Okay, so yeah, so just remember that this is how you do the shared memory in the operating system. Okay, so now we're going to talk about how we'll talk about the thread model for OpenMP. Okay, so there are other thread models, but for OpenMP, this is based on the fork join model. Okay. So the fork join model is we start with one single thread, okay, called the master thread, and it's going to do a bunch of work until eventually it gets to some point where it realizes that there's a lot of work that can be done in parallel. Okay, so in the beginning, the master thread is going to do some type of sequential work. For example, it might read some files, or it might initialize some data structures or something like that. Okay, but at some point, maybe it gets to like a big computation, right? And then at that point, it wants to parallelize the work. Okay, so then at that point, it's going to create a bunch of parallel tasks, right? And then these tasks can be assigned to multiple parallel threads, right? So you could have more tasks than threads, right? Or you could have more threads and tasks, or whatever. But in any case, you have several tasks here. Okay. Eventually, these parallel tasks they manage to finish the work that needs to be done, right? And then the tasks join back together, and then you end up with one thread again. Okay. So that one thread is going to execute some more, and then maybe later on, it again gets to a spot where it needs to have some parallelism, and it's again going to fork into multiple ones of these parallel threads. Okay, so the process is that we keep forking into multiple threads, right? And then eventually, when the parallel work gets done, the threads join back together into a single thread. Okay, yeah. So okay, so next. Okay. So I want to mention that it's possible for so the master thread can fork off these slave threads, right? But it's also possible for the slave threads themselves to sort of recursively create more threads. Okay. So for example, over here, right, we have the master thread creates two threads, right, and then these two slave threads can create even more threads. Okay, and then these sort of sub threads here, right, when they join back into one of these slave threads. And then eventually the two slave threads join back into the master thread. Okay, and then so here, whenever you create a thread, right, eventually the thread finishes and then joins back together with all of the forked threads, right? But you don't have to do that. You could create these detached threads that just sort of execute on their own, and they don't do a join when they terminate. Okay, so this fork join model actually can capture many types of parallelism that we care about in practice. Okay, so for example, if you consider the merge sort algorithm, right? So remember the way that merge sort works is we're trying to sort all of these numbers over here, right? And then you just so this is an array of numbers. You split the array into two parts, right? And then you recursively sort each part. Okay, and then you keep splitting until the arrays get small enough. And then you sort that small array, and then later on you merge these sorted arrays back together. Okay, and in the end you get that everything is sorted. So if you want to run this type of algorithm in the fork join model, then initially, right, we would have a master thread, right? So maybe that master thread like sort of reads this array from a file or something, right? So it does some sort of sequential work. And then now, when the master thread wants to start sorting these numbers, right? So now there's parallelism involved. So the master thread can actually fork off to another thread. Okay, so maybe the master thread continues over here, right? So let's say this is the master thread, right? And then he's going to fork off a slave thread. Okay, right? And then the slave thread, as we said, can recursively fork off more threads. So then, for example, this slave thread here can maybe because this array here is, let's say, too large for the slave thread to sort by himself, right? He can again fork another thread. So, so the slave thread takes half of the array, right? And then he forks a thread, and then that takes another half of the array, right? So that's slave number 2, right? And then the master thread here, he can also subdivide the work, right? So he can take, let's say, half the array, and then he can give another, the other half to, let's say, a third slave thread, okay? And then you just keep you keep forking off threads as long as you need to, right? So maybe here, once we're down to like a race of size 2, then the slaves can just sort them themselves. Okay, so we're not going to do any forking over here, but then eventually, after the slaves have sorted their own subarrays, right? Then they need to merge back together, right? So here you have S2 is going to join back together with S1. Okay, so And then here, the S3 thread is going to join back together with the master thread. And then here, right, you have that so we have S2 here, right, and then you have S1, and then you have the master thread, and then you have S3, and they're doing a join here, right? And then here you have the first slave thread is going to join back with the master thread, okay? And then after that, we're done with the computation, and so the master thread can just keep continuing. Okay, so so this fork join model can actually capture a lot of different types of parallelism. Yeah, so it's even though it's not the only model for parallelism, it's a very useful model. Okay, so next we're going to talk about executing some things that we need to be aware of when we execute shared memory programs. Okay, so the first thing is that we need to think about how are these threads actually working together, right? Physically, what is happening? So so physically, if you just have a single thread, okay, and then you have a program, then so the program is just a bunch of lines of code, right? So the single thread is just going to go through these lines of code one by one, right? Now sometimes it can loop, of course, right? But basically, it's just it's executing these the instructions exactly in the order that the program was written. Okay, now when you have multiple threads, then what's going to happen is, for example, here we have 2 threads. Okay, so each thread has a sequence of instructions that it wants to execute. But when you execute these 2 threads together, right? Physically, what's going to happen is that these 2 instruction streams need to get interleaved somehow, right? Because, for example, this might happen at time step, let's say, time equals 1 second, okay, right? And maybe this instruction happens at time equals, let's say, 1.5 seconds, okay, right? And then this might happen at time equals, let's say, 3 seconds, right? This happens at time equals like let's say 3.5 seconds or something, okay? So then physically, what's going to happen is that this instruction happens first, right? And then this one, right? Because it happens at 1.5, right? This, and then this one, and then that one, okay? Now, of course, there's no fixed order that these instructions happen in, okay? They can actually interleave in any order, okay? So for example, maybe this instruction actually happens at 3 seconds, okay? And then this one over here, right? Maybe it happens at 2 seconds, okay? So in that case, we would do this one first, and then that one, and then this one, and then this one, okay? But in any case, there's some sort of actual interleaving which happens when you execute these 2 threads together. Okay, so this is one possible interleaving, and there are many other possible interleavings. So now the fact that the threads, their execution is interleaved with each other, okay, this can actually cause lots of problems. Because if the so sometimes if you don't write a correct program, then depending on which interleaving you have, the program might actually have a bug. Okay, it could be that the program works fine in some interleavings, but if you change it to a different interleaving, then the program behaves incorrectly. Okay, so if there is such a situation, then we say that there's a race condition for this program. Okay, because the correctness of the program depends on the interleaving that occurs. And since we have, we as a programmer have no control, the programmer, the user, so usually we have no control over what interleavings are actually going to occur, okay? Then if the program actually misbehaves under some interleavings, right, then that program is incorrect, right? We can't use that program, because if you give this to a user and then you happen to get this bad interleaving, then your program's going to do something incorrect. Okay, so yeah, so in fact, writing correct programs, correct concurrent programs that work for all interleavings, okay, this is actually quite challenging. And in fact, it's one of the main challenges to writing shared memory programs. Okay, so let's see what kind of errors can actually occur, what kind of the race conditions can actually occur, okay? So I'm going to give a simple example here. So usually these errors occur when the different threads access a shared piece of memory, okay? If they're all accessing completely different pieces of memory and the threads are not interacting with each other, then there's basically no way for one thread to interfere with another thread. Okay, so in that case, nothing bad can really happen, right? As long as the individual threads are working correctly, then if they don't interact with each other, then nothing bad can happen. Okay, the only time when bad things happen is when they interact by sharing pieces of data. Okay, so now, so the example we have is, suppose you have two threads which are doing something very simple. They just take a value, right, and then they increment it. Okay, so both threads are sharing a value x. Okay, and they both want to increment the value. So, for example, if the value starts at 0, right, then if both threads increment it, then x should become 2 at the end. Okay, but let's look at what happens if you run these two threads concurrently. Okay. Okay, so then the problem here is that when you run these two threads concurrently, even though the only thing we want to do is to increment the variable, this actually involves multiple substeps. Okay, the increment doesn't just happen atomically. There are several steps that we need to do. So the first step is that so the variable is going to be stored in memory somewhere. Okay, and so in order to increment it, we first need to read the variable from memory into the register that a thread is using. The registers for the processor that a thread is using. Okay, so thread 1 and thread 2, right? They each have some registers for doing their computations. So thread 1 is first going to load x from memory into its register, right? So let's write this as like R1 here, right? So it's going to load this into register 1, okay? And then, let's say that x initially was equal to 0, okay? Right. You know what? I'll do this a bit later. Okay, oops. Yeah. So so first we load x into the registers, and then next we're going to increment x in the register. Okay, and then finally, you write back the value of x from the register back to memory. Okay, and thread 2 is going to do the same thing, right? It also loads x from memory into thread 2's register, right? It increments it in its own register and then writes it back to memory. Okay, so now since you know, each thread is doing several instructions, they can be interleaved in some arbitrary order. Okay, so suppose that we have this thing on the right as the interleaving. Okay, then what's going to happen is that, so now let's look at what the value of x is going to be at the end if we have this interleaving. Okay, so with this interleaving, so the first thing we do is thread 1, right? So that's thread 1 is indicated by these black operations, and thread 2 is indicated by these blue operations. So thread 1 is first of all going to load x into its register 1, let's say, right? So if x initially was equal to 0, then now we have register 1 is equal to 0. Okay, and then it's going to increment x. So now register 1 is going to be equal to 1. Right? It's going to increment x in its registers. So now R1 equals 1, right? And then next, suppose at this point, thread 2 does its operation, its first operation. Okay, so then now thread 2 is going to load x into its register, R2, let's say, right? So then now we have, now at this point, x is still equal to 0 in the memory, right? Because here, what we've done, what thread 1 has done is just to increment the value of x in thread 1's register, right? In the memory, x is still 0. So therefore, when thread 2 loads x, right, it's going to set its register to be equal to 0. Okay. Next, let's say we go back to thread 1. So that's going to store the data from R1 back into the memory. So now x equals 1. Okay. All right. Then next, we go back to thread 2. And he's going to increment the value of x in his register. So now we have R2 equals 1, right? And then he's going to write back the value of R2 to the memory. And so x is at the end going to equal 1, okay? Because R2 thread 2 is writing back the value 1. Okay, so we see that at the end of all this, right, the value of x is 1. Okay, but this is incorrect, because intuitively what we wanted to happen was that since you have two threads doing two increments, we wanted the value of x to be equal to 2 at the end. Okay, so this is an example of a race condition where the program behaves incorrectly in certain interleavings. Okay, so then how do we deal with this situation? So if we're using a library, right, with some routines, with some pre-written routines, then we say that a routine is thread safe if it can be called from multiple threads at the same time and not produce any bugs. Okay, so basically this routine should not have any race conditions in them. Okay, if it doesn't have any race conditions, it's a thread safe routine. Okay, so for example, many I/O routines are written so that they're thread safe. Okay, so for example, if you do something like a printf, okay, if you do printfs from two different threads, right, then if the printfs are not thread safe, then the message being printed can be sort of garbled, can be mixed in together, right? But if the printf is thread safe, right, then you're going to see a complete messages being printed by each thread, right? You're not going to get the different outputs to be garbled with each other. Okay, but there are certain routines that you have to be careful about that are not written to be thread safe. Okay, so those routines can only be correctly used by one thread at a time. Okay, so for example, there's some random number generators that are only going to produce really good random numbers if they're only being used by one thread at a time. Okay, if you have several threads all calling the random number generator at the same time, right, then you could get outputs which are not really random. Okay. Yeah. So as I said, usually these race conditions are going to occur. Well, they only occur if we have accesses to shared variables. Okay, so whenever we have multiple threads accessing, like let's say, a shared data structure, okay, then we have to be very careful about how we write these programs. Okay, so the way that we can write a program which can work correctly even with multiple threads, so one way is to use something called a critical section. Okay, so there are other ways also, and I'll talk about those in later lectures. But today we're going to see how to use critical sections to ensure the correctness of these programs. So a critical section is it's a piece of code that can only be executed by one thread at a time. Okay, so because this code is only being executed by one thread, then that thread can make multiple changes to the data without being interrupted by any other thread. Right? As long as the code is in a critical section, there's only one thread that can be executing that code. Right? Nobody else can touch that code in the meantime. Okay, so yeah, so this is also called mutual exclusion, right? Because the different threads exclude each other, mutually exclude each other. Okay, so there are many ways to use critical sections. So, for example, Java has these synchronized statements, and they implement critical sections. Okay, and many other programming languages and operating systems also have ways for the programmer to use critical sections. Okay, so the critical section helps you avoid the race condition bugs that we saw. Okay, so for example, we were trying to increment a value. Okay, so that consisted of several operations. Now, if we put all of these operations into a critical section, right? So that would mean that these three operations would have to happen. So if one thread was doing these operations, right, then it won't be interrupted by any other thread. Right? It'll do either the thread will do all three operations, or it won't do any of those operations. Right? It's not like the thread can do, let's say, 2 of these operations and then suddenly get interrupted by some other thread. Okay, so now if this piece of code was actually in a critical section, then when you run these 2 threads together, what are the interleavings that you could get? Okay, so for example, you could get this type of interleaving, right, where thread 2 does everything, does this entire piece of code, and then thread 1 does this entire piece of code. Okay. Now, in that case, we actually get that the value of x is correct at the end, right? Because here, you load x, you increment it to 1, and then you store 1. And then so here, thread 1 is going to read x as 1, right? And then he's going to increment it and then store 2 back into x. Okay, right? So and then even if you have thread 1 go first, okay, so if these black operations happen first and then the blue ones, right, you would still have x equal 2 at the end. Okay, so as long as all 3 operations happen together without interruption from any other threads, right, then the program is going to work correctly. So yeah, so this is how we achieve correctness in concurrent programs, is by putting certain blocks of code in these critical sections, so that we can go from like one. So if before you start the critical section, suppose the program is in a correct state, okay, then because you can execute the entire critical section by yourself, then afterwards the program transitions to another correct state. Okay, so then the program always stays in correct states. Okay, all right, so locks are locks are a way for ensuring mutual exclusion. Okay, so the way locks work is that before a thread enters a critical section, it sets the lock, okay, and then it unsets the lock after it leaves the critical section. Okay, so now these locks have certain properties. So the property is that if the lock is open, then a thread can set the lock, okay, and then the lock becomes locked, okay. But if a thread tries to use the lock and the lock is already locked, right, then the thread won't be able to do anything. It'll just block, okay. It'll have to wait until the lock is unset, okay. Yeah, so therefore, if you have a lock which protects this critical section, then only the first thread to set the lock, right, can actually can successfully set the lock, and then it can go execute the critical section. Okay, the second and all the later threads that come, right, they're going to find the lock is already locked, and so they need to block at the lock, right? So they're going to wait at the lock, and they won't be able to do the code in the critical section. So this way, there's only one thread doing the critical section at a time. Yeah, right. And then the first thread to come that actually set the lock, right? Then eventually, let's say it finishes all the operations in the critical section, and then it unsets the lock. Okay. And at that point, all of these waiting threads, right? Then they can all of them can compete with each other to try to set the lock again. Okay, so one of those competing threads will actually successfully set the lock, and then that thread can do the critical section. Okay, the other threads that don't manage to set the lock, they're going to block again. Okay, so they're going to wait again at the lock. Yeah, so this would be like the piece of code that you would have. Okay, so before you do this critical section, that so here is what where you want to ensure that only one thread is doing this at a time, right? So you have multiple threads that are going to come to this lock. They all try to lock, right? So but only one of them will succeed and then go into the critical section. Okay, so the other guys are just going to be blocked here. Okay, and then eventually this guy is going to finish, right? And he's going to unset the lock. And once the lock is unset, right, then these two waiting threads can again compete to get the lock. One of them gets the lock. Let's say the third thread over here, right, and then he can go into the critical section. But then thread 2 is again blocked. Okay, so this way we always just have one thread at a time in the critical section. Okay, so next we're going to talk about, so when you use locks, so this is a way to ensure the correctness of your program. Okay, but you got to be careful about how you use the locks, because if you don't use them the right way, then one bad thing that can happen is your system can deadlock. Okay, so then all of the threads will be blocked. Okay, so of course you don't want that. You want to, so the purpose of the lock is to make sure that one thread gets to make progress while the other threads are blocked. Okay, but when you have a deadlock, everybody is blocked. So then your program is just stuck forever. Okay. So then when can you get, what kind of situations lead to deadlocks? One example is if a thread needs multiple resources, right? So let's say that you have two threads over here, T1, T2, right? And they both want to lock two resources. Now, if T1 locks R1 first, and then T2 locks R2, right? Then because T1 needs two resources, T1 will try to lock R2. Okay, but T1 won't be able to get R2 because T2 has already locked R2, right? So therefore, T1 is going to block, right? Likewise, T2, after it gets R2, it also wants to get R1, okay? But T2 can never lock R1 because T1 has already locked R1. So therefore, T2 is also going to block. It's also going to wait, okay? So now you see that both T1 and T2 are going to end up waiting forever, okay? Because both of them have one of the resources that they need, right? But they can't get the other one. So they need to just keep waiting for the other one, but the other resource never becomes available. Okay, so yeah, so we can, so here's an example where we have a cycle of two threads where they wait for common resources. Okay, so you could actually have examples where you could have cycles of more than two threads. Okay, so for example, this traffic situation here, this is also an example of deadlock because you see that none of the cars can move, right? This entire intersection is blocked, and basically you can think of this in terms of threads and resources. So for example, you can think of these roads as being resources. Okay, so maybe you have like one resource here, right? So to get across this road, okay, you actually need two resources. If you're going in this direction, you need two resources. You need to get through this intersection and this one, okay? Now, if you want to proceed in this direction, you also need two resources. You need to get resource number 2, and also you need to go through, let's see, let me redraw this. You need to get through this part over here, okay? And then if you're coming from this direction, right, you need to get resource number 3, and also there's a resource over here. Okay, and then finally, if you're coming from up top here, right, you need to get resources 4 and 1. Okay, so now you see what's happened is that each of these, so you can think of these 4 directions of travel as being 4 threads, right? So each of the 4 threads has gotten 1 resource, but it needs 2 resources, but it'll never get the second resource because that's already been taken by somebody else. Okay, so now these guys are just stuck over here. Okay, so now if you get one of these stuck situations, okay, basically the only thing you can do is you got to make somebody back up. Okay, you got to basically reset the system. So for example here, right, some of the cars are going to need to like reverse. Okay, like if these guys reverse, right, then that's going to clear up this lane of traffic, and so then these guys can go, and then the other lanes can go. Okay, but you need to reset the system somehow if you ever get into a deadlock. So of course it would be better just to avoid deadlocks in the first place. Okay, so now one way that you can avoid deadlocks is if you have these 2 resources, then the problem here was that T1 locked R1 first, and then T2 locked R2, right? And then after T2 locked R2, it tried to get R1. Okay, but by that point it's already too late because R1's been taken by T1. Okay, so instead you should have one way to avoid deadlock is for all the threads to lock the resources in the same order. Okay, so instead of locking R2 first, right, both T1 and T2 should try to lock R1 first. Okay, if they both try to lock R1 first, right, then what's going to happen is, so T2 does not try to lock R2. Okay, it tries to lock R1. So since both T1 and T2 are trying to lock R1, only one of them will succeed, and the other one will wait. Okay, so let's suppose that T1 succeeded. Okay, so then T1 gets R1, and now T1 can go get R2, right? Because that's not been taken by anyone yet. So then T1 can go get R2, and then once it's got both resources, it can go do its operation. Okay, and then eventually T1 is going to finish its operation, and then it's going to release both R1 and R2. Okay, so it's going to release both R1 and it's going to release R2, right? And at that point, T2 can get R1, right? And then it can also get R2, right? And then that way T2 can proceed. Okay, so if we ensure that the threads lock the resources in the same order, then these problems won't happen. Okay, now in practice, it's not that easy to ensure threads lock resources in the same order because, for example, one problem is that maybe a thread doesn't know which resources it needs at the beginning. Okay, so maybe it initially, let's say T1 knows that it needs, initially, let's suppose that T1 knows it needs R1, right? And then T2 knows it needs R2. Okay, but at the beginning, maybe T1 doesn't know it needs R2. Right? And T2 doesn't know it needs R1. Okay, so then in that case, T1 is going to lock R1, T2 is going to lock R2. But then later on, if they try to lock the other resource, again, they'll be stuck. Right? Yeah. So the reason this locking resources in the same order, the reason this doesn't always solve the problem is because, for example, you might not even know which resources you need, so you can't get them in the right order. Okay, so therefore another so if we can't always lock resources in the same order in order to avoid deadlock, then something else we can do to avoid deadlock is that we can use these non-blocking locking primitives. Okay, so basically these primitives or these functions try to get a lock, but if they fail to get the lock, then they're not going to block the thread. Okay, then the thread can still go do something else. Okay, so the way this works is that suppose you have this non-blocking function called test lock. Okay, so test lock is that we try to get so the lock here is called mutex. Okay, so we try to get this mutex lock. If we get it, right? So if flag is let's say if flag is 0, okay, then this means that we actually managed to get the lock, right? So then we can go into the critical section and do all this stuff. Okay, and after we're done with the critical section, we can unset the lock. Okay. However, if the lock has already been taken by somebody else, then the flag is going to be 1. Okay, in that case, we're going to go into this else part, but we're not going to, the thread is not going to just block at this function here. It's going to jump into this else part, and it can do more stuff down here. Okay, so this means that the thread is not stuck at the, it's not stuck trying to get the lock. Okay, yeah, so so that's how this works. Let's see. Right. So then, if the thread, so this thread wanted to get the lock, and it called test lock, and it failed to get the lock, right? So it jumped into the else part, right? So then later on, the thread can maybe go back to this test lock and try to get the lock again. Okay. So maybe at that point, whoever was in the critical section is already finished, and he released the lock, and now the thread can actually get the lock this time. Okay. So the thread just keeps keeps coming back and trying to get the lock. If it fails to get the lock, that's not really a problem. The thread will not become stuck, right? It'll just go do something else. Okay, so so next we're going to talk about the performance implications of using critical sections. Okay, so sometimes you have to use critical sections in order to make sure your code works correctly. Right. So so safety first, right? We need to make sure that the code is safe and works correctly. Okay. However, you don't want to overuse critical sections, right? Because if you use a lot of critical sections, then yeah, it's true that your code works correctly, but it might also perform very poorly. Okay. And the reason is that when you use a critical section, you're actually going to serialize your code. Okay, so the reason is that if you have a critical section here, right, then only one thread can run this critical section at a time. Okay, so if you have several threads that all need to go through this critical section, right, then they have to go through the critical section sequentially, right, one after another, right? You see that there's no parallelism whatsoever in the critical section. Okay, so therefore, if you make a very large critical section, right, then it's easy to ensure your code is correct in that case because everything is in the critical section. But because everything is in the critical section, you don't have any parallelism. Okay, so yeah, so you do need to use critical sections, but you want to make them sort of as small as possible to ensure that your program is correct. And as long as your program is correct, you don't want to make them. You don't want to make these any larger. Okay, so next we're going to talk about condition variables. So these variables are used with critical sections. Right, so the idea is that sometimes you should only execute a critical section when a specific condition occurs. So I'll give you an example of that later. Okay, but in these situations, we want to use a condition variable. So the way this works is that a thread is going to get a lock for a critical section. Okay, but it should only execute that critical section when the condition occurs. Right. So after the thread gets the lock for the critical section, it's going to call the condition variable. Okay, and then if the condition is true, right, then the thread can go do the critical section. But if the condition is false, then the thread should wait until the condition becomes true. Okay, and now when the thread is waiting, right, you don't want the thread to keep the lock. Right? Because if it's keeping the lock, then that's blocking all the other threads from potentially using the critical section. Okay, so when the thread is waiting, right, it's actually going to go to sleep, and then it's going to release the lock. Okay, so and it does both of these things atomically. So by going to sleep, that just means that the thread is going to just stop and not do anything. Okay, because the thread is waiting for the condition to become true. Right, so it's got nothing to do before the condition becomes true. Okay, and in fact, you could have several threads which are all waiting for this condition, right? So in that case, we can put all of these guys into a queue. Okay, so we can just have some way of keeping track of all of these waiting threads. Okay, now eventually, let's say that this condition becomes true. Okay, so at that point, we're going to have a signal occur. Okay, so the signal is going to tell all of these waiting threads that now the condition has become true. Okay, so now since we have this condition holding, all of the threads are going to wake up, right? And after they wake up, they try to reacquire the lock. Okay, and of course, since they're competing for a lock, then only one of the threads can succeed. Okay, now the reason we use a condition variable is that this is more efficient than continuously testing a lock to see when the condition gets met. Right. So if the condition is false right now, then I might as well just go to sleep and wait for the condition to be true, right? Instead of me testing over and over whether this condition is true. Okay, so to use these condition variables, we have a few functions, right? So we have this wait function. So this is called by a thread which currently has the lock, right? And now he wants to check whether this condition is true. And if it's false, then he's going to go to sleep. Okay, so the signal function is going to signal that a condition has become true. Okay, and then once the signal occurs, then all the threads waiting on that condition, they wake up, right? And then they try to reacquire the lock. Okay, so this so the signal maybe just signals one thread to wake up, but we can actually signal multiple threads to wake up, or actually all threads to wake up using signal all. Okay, so let's do an example of using these condition variables. So this is going to be the producer-consumer example. Okay, so what's happening here is that we have these a bunch of consumer threads and a bunch of producer threads. Okay, and then they all access this queue. Okay, now so the producer threads are going to put stuff into the queue, put items into the queue. Okay, and the consumer threads remove items from the queue. Okay, so they just keep doing this. However, if the queue is currently empty, right, then the consumer threads have nothing to remove. Okay, so then the consumer threads have to wait. Okay, so if you're a consumer thread and you try to take something, then the condition is that the queue has to be non-empty. If the queue's empty, then you have to wait. Okay, and on the other hand, this queue has a capacity, right? Let's say you can put 100 things into the queue. Okay, so if the queue is already full, if it's already got 100 items, right, then the producers have to wait. So if you're a producer thread, right, then your condition is that the queue, in order for you to put something into the queue, the condition is that the queue is not full. If it's currently full, then you have to wait until the queue becomes non-full again. Okay, so so one way you can you can solve this problem is that the producers and the consumers, right? So whenever they access this queue, then because the queue is being shared between multiple threads, the threads need to lock the queue. Okay, but if you lock the queue, then to solve this producer-consumer problem, what you can do is you lock the queue, you check if it's empty or full. Right? If you're the producer, you check that the queue is not full. If you're the consumer, you check it's not empty. Right? But if your condition fails, right, then you can unlock the queue. Right? But then later on you have to come back and recheck that condition. Okay, so in fact you have to check this condition over and over, and each time you check it, you have to try to get the lock again. Okay, and this is actually an expensive process to acquire the lock. Okay, so this process of getting the lock, checking the condition, and then releasing the lock, and then doing that over and over, this is actually very inefficient. Okay, so a more efficient way to do this would be the following. Okay, so here we have the code for the producer threads and the consumer threads. Okay, so let's just briefly go through this. So the producer thread is, so he's trying to place items into the queue. Okay, so because it's a shared queue, then he needs to first lock the queue in order to get access to it. Okay, so he sets the lock, and then now he checks whether the number of items in the queue is equal to n, which is like the maximum number of items you can put in there. Okay, if it's less than n, okay, then the queue is not full. Then the producer can just increase the number of items, right? And then he's also going to send a signal to all the consumer threads that because he's put an item into the queue, then this queue is not empty. Right? He's going to signal all the consumers about this. Okay, and then after that he's done. Right? So he's put his items in there, or put his item in there, and then signaled all the consumers. So now he's done, and he can release the lock. Okay. On the other hand, if when the producer was trying to put an item into the queue was already full, okay, so items equals n, right? Then the producer needs to wait in order to put his item into the queue, okay? He needs to wait until the signal that the queue is not full anymore, okay? So he's waiting on the signal. And when he's waiting, right, so currently the producer has the lock on the queue, so nobody else can access the queue at all, okay? So now if the producer keeps this lock on the queue, okay, then because the queue is full right now, and because nobody else can access the queue because this producer has a lock, right, then nobody can ever take anything out of the queue, and so the queue will always be full. So that means that the producer will be waiting there forever. Okay, so therefore the producer has to give up the lock to the queue, okay, in order for other threads to go take something out of the queue, right? And then only after other threads have taken something out of the queue can this producer put his item into the queue. Okay, so this is why the producer has to make sure that when he's waiting for this not full signal, right, he has to give up the lock. He has to release the lock over here. Okay, so that's the producer's actions. And now for the consumer, it's sort of like the opposite of this. So the consumer, to get to access the lock, right? So the consumer is trying to take something out of the queue, okay? And to do this, he's got to first lock the queue, right? And then he checks whether the queue is empty or not. Okay, so if items equal 0, then the queue is empty. Okay, now if items is not 0, right? So items will be larger than 0, then the consumer can go over here and he can just take an item out. Okay, he decrements the number of items. Okay, and then now since he's taken one item out, he can send the signal that the queue is not full anymore. Okay, so for example, remember that these producer threads were waiting for the signal to happen. Okay, so this consumer thread has been very nice. He's taken an item out of the queue, so now we know the queue is not full anymore, and the consumer is going to signal any potentially waiting producers about the situation. And then the consumer is done, and he can release a lock. Okay. However, if this consumer, when he was trying to take some items out, if the queue was already empty at that point, okay, then the consumer needs to wait until the queue becomes non-empty, right? And to do that, again, the consumer also needs to give up the lock, because if the consumer holds, so the consumer currently at this point he has the lock, right? Because in order to get to this point, he had to set the lock. Now, if the consumer just keeps the lock at this point, then the queue will stay empty forever, right? Because nobody can access the queue in order to put something in. So then the consumer is going to be waiting here forever. Okay, so the consumer needs to give up the lock to release the lock, and then wait for the not empty signal. Okay, so yeah, so now let's go through one possible execution for this. So suppose you, so what could happen is, yeah, so let's say that we have a queue over here, right? A queue like this, right? And then suppose the queue is currently empty, okay? So then we have a consumer thread waiting at the queue, right? He's waiting for this queue to become non-empty, but it's currently empty, so this consumer thread needs to wait. Okay, and then right. So the way this consumer thread executed was that he first set the lock. Right. He checked whether the queue is empty. It is empty. Right. So he gives up the lock. Okay. So now when the consumer 1 is waiting, the lock is actually free. Okay. So now because the lock is free, you could have another consumer come over here. Right. So he also sets the lock. Right. He also checks whether it's empty or not. It is empty. Right? So then this consumer 2 is also going to start waiting, right? And when he waits, he's going to release the lock. Okay, so then later you could have a producer thread come, right? And then this guy is going to put, so then he's going to try to set the lock. So the lock is currently free because both C1 and C2 have released the lock. Okay, so P1 can get access to the lock, right? He can like stick an item in here, right? So the producer comes, he sets the lock, he checks whether it's full or not. It's not full because there's nothing in the queue, right? So then he goes over here, adds an item, and then he sends the signal. Okay, so so the signal is going to sort of alert these two guys. Oops, right? So currently the C1 and C2, right? They're like sleeping. Okay, so they're like they're sleeping. Okay, like sort of like Z's like that. Okay, but once P1 sends the signal, right, then these guys are gonna like wake up, okay? Right. When they wake up, they try to reacquire this lock, okay? Now currently P1 has the lock, okay? So both these C1 and C2 cannot acquire the lock yet, okay? But after P1 sends a signal, he's gonna release the lock, okay? So now the lock is free, right? And then P1, let's say, goes away after this, okay? And now C1 and C2, they're both trying to acquire the lock, okay? Now let's say that C1 gets the lock, okay? So then he gets the lock, right? So I'm going to circle him, right? And then C2, because he doesn't get the lock, right? Then he's going to be blocked, okay? So C1 gets the lock. He's going to go over here. So C1 wakes up. He gets the lock. And now C1 is actually in this part of his execution right now. Okay, so he's in the while loop. Okay, so after he gets the lock, he's actually going to go back to the beginning of this while loop. Okay, he's going to check whether items equals 0 again. Okay, so currently there's one item in there, so actually items equals 1. So therefore C1 can go over here and he can decrement items. Okay. And then he's going to send his signal of not full, and then he releases the lock. Okay, so after he releases the lock, remember that C2 here was still blocked trying to get the lock. right? So because after C1 and C2 waked up, right, they were both trying to get the lock. Okay, C1 got the lock, but C2 was blocked, right, trying to get the lock. Okay, so now C2 has managed to get the lock because C1 released it. Okay, so now C2 has managed to, right, so C1 has actually taken the item out. Yeah, sorry, I forgot to say that. So now C2 gets the lock, right? But notice that C2 is still here in his code, right? So even though he got the lock, because he's here in the code, then before he goes on, he needs to go back to the beginning of this while statement, right? So he needs to check whether items equals 0 again. And in fact, right now, items again is equal to 0, okay? Because C1 took out the only item, right? So now items, the number of items is 0 again. Okay, and because it's 0, then unfortunately C2 is going to have to go back to sleep. Okay, he's going to have to wait until the not empty signal happens again. Okay, and when he goes to sleep, he's going to give up his lock. Okay, so by the way, this example shows you why here we need to have a we need to have a while statement here. Okay, it's you know, if you write this code, you might think that, okay, all I need to do is just have an if statement here and check whether the number of items is equal to 0. Okay, but this is not sufficient because because if you just have an if statement over here, then after these waiting threads wake up, right, they're not going to recheck whether items equal 0 again. Okay, so so after C1 and C2 wake up, they're both just gonna try to take an item, okay, which would be incorrect, right? Because only C1 should be able to take the item, right? C2 needs to wait again. Yeah. Okay, so so that is the example of how to use condition variables. So next, we're going to see how to use or how all these concepts come up, and we're going to talk about how to actually do the programming using OpenMP.